This project is about the understanding of fundamental electrochemistry and its application in the real world. Here at NanoFlex we've been developing nanoscale electrodes for the last 7 years, and we are now at a point where we are selling electrodes commercially.
The project involves fabrication, characterization and fundamental studies of nanoelectrodes made of different materials and a range of sizes. The aim is to manufacture sensors and batteries using NanoFlex technology.
Nanoelectrodes are exactly what they sound like. They are electrodes where one of the characteristic dimensions of the device is on the nanometer scale. So for the sorts of devices that we're looking at with NanoFlex, we're talking about the width of the electrode tends to be on the sort of 100 to 10 nanometer scale. So you're looking at less than a millionth of a meter. That size range bestows peculiar properties on nanoelectrodes. Electrochemical devices are widely used as energy storage devices and as electrochemical sensors. Moving into the nanometric regime results in electrode systems that are both faster responding and in which we can store orders of magnitude greater levels of energy than we would on the macroscopic analogues. And we don't fully understand why this is the case. So this project is concerned with trying to understand why these phenomena exist, why you see these super fast reactions, why you see these super high levels of energy storage, so that NanoFlex can design and manufacture more reliably and more robustly devices for those purposes.
The international market for this work is quite profound. Every country in the world is concerned about its environment and how it controls and protects it. And electrochemistry, both in research terms and in terms of application terms, spreads far and wide across the globe. Well, there are a number of environmental benefits, especially in terms of policing and monitoring our environment, but also in terms of the materials used. We'll be using far less material than we used in a conventional electrochemical electrode, for example. So for scarce resources such as platinum, which is an important noble metal in electrochemical work, we get down to less than 2 cents of platinum per unit electrode.
The advantages are obviously that it's very real world. SMEs tend to work further up the technology readiness level than might usually be the case within an academic environment. So you're very much looking at developing technology which can be easily transferred over into the product space. So you're very much looking at sort of like TRLs 5, 6, 7, and that's quite an exciting place to be in terms of later on down the line, actually seeing something going out onto the shelf that you know you've contributed to an understanding of how it works and in the development of its design.
Because when you're in the academic side, you only see the fundamental studies. I mean, you never see if you can get something like a device to manufacture and to commercialize it. So you feel that you are doing something for the society.
The research that Miriam's doing will benefit NanoFlex by providing us with answers to some highly important questions regarding the performance of our electrodes, particularly at the very small scales, and this will provide benefits to a wide range of potential end users, including those interested in environmental monitoring and monitoring at legal levels, and also in vitro diagnostics where biomarkers are only available in very small amounts.